The James Webb Space Telescope, often called the successor to the Hubble Space Telescope, has completely transformed how we think about the universe. Since it became operational, the JWST has given us jaw-dropping views of space, revealing things we never thought we'd see. With its cutting-edge tech, scientists can now explore the farthest reaches of space, observing stars and planetary systems that formed billions of years ago. To understand why the JWST is such a big deal, we have to look back at its legendary predecessor, the Hubble Space Telescope. Launched in 1990, Hubble gave astronomers their first crystal-clear images of deep space. Orbiting above Earth's atmosphere, it avoided the atmospheric distortion that blurs telescopes on the ground. Hubble made huge contributions, like measuring the universe's expansion rate and capturing a comet smashing into Jupiter. Its deep field images, showing light from galaxies billions of light-years away, gave us an early glimpse into the distant universe. But Hubble had its limits. Its mirror was only 2.4 meters wide, which restricted the amount of light it could collect. Plus, it mainly observed ultraviolet, visible, and a bit of near-infrared light. As our questions about the cosmos grew, it became clear we needed a new telescope, one that could peer deeper into the infrared spectrum, cut through the cosmic dust, and uncover the universe's first galaxies. Planning for the JWST began in the mid-1990s, even before Hubble had reached its peak. Named after James Webb, NASA's administrator during the Apollo missions, this new telescope was designed to see further back in time than ever before, to capture light from the first stars and galaxies formed after the Big Bang. Designing the JWST was a massive engineering challenge. Unlike Hubble, which orbits Earth, JWST is positioned about 1.5 million kilometers away at the second Lagrange point, or L2. This location offers a stable environment with minimal interference from Earth's heat and light. But it also meant there'd be no way to repair it once launched. Everything had to work perfectly. To collect more light and see fainter, more distant objects, JWST needed a much bigger mirror. The solution, an enormous 6.5-meter wide mirror made of 18 hexagonal segments crafted from beryllium and coated in gold. Since it was too large to launch fully open, the mirror had to be folded up and then unfolded with nanometer precision in space. Another key component is its sunshield, a 5-layer structure the size of a tennis court made of a special material called Kapton. This sunshield protects the telescope's instruments from heat and light, keeping them extremely cold, just a few degrees above absolute zero. That temperature is critical for observing faint infrared signals. After years of development, delays, and a budget of nearly $10 billion, JWST launched on December 25, 2021. Watching the telescope's deployment was like a high-stakes space ballet. First, the sunshield unfolded, an intricate dance involving thousands of components. Then the mirror segments were released and aligned with incredible accuracy. By mid-2022, the telescope was ready, and its first images blew scientists and space enthusiasts away. Seeing the universe in infrared brought unprecedented clarity and detail. One of JWST's main missions is to study the first galaxies that formed after the Big Bang. Because the universe is expanding, light from these galaxies shifts into the infrared, a phenomenon known as redshift. Hubble could detect some of these early galaxies, but JWST's advanced infrared capability lets us study them in far greater detail. One of its earliest surprises was discovering galaxies that existed just a few 100 million years after the Big Bang. What shocked scientists was how mature and massive some of them appeared, way earlier than anyone expected. That discovery challenged long-standing theories that galaxies started small and slowly merged over time. JWST's data suggested some galaxies formed rapidly and reached significant sizes far earlier than models predicted. This has forced astronomers to revise their understanding of how the universe evolved. Another breathtaking view came from its observation of the cosmic web, a vast network of dark matter and gas that connects galaxies across the universe. JWST revealed fine details of this enormous structure, showing how galaxies grow along these filaments and how dark matter influences cosmic architecture. JWST also gave us new insight into how stars form. It can see into dense clouds of gas and dust that block visible light but are transparent in infrared. One notable region it observed is the Orion Nebula, a stellar nursery located about 1,344 light-years from Earth. The images showed newly forming stars, some still wrapped in their dusty cocoons, providing a better understanding of how stars and planetary systems come to life. It also captured stunning images of the final stages of stars, such as white dwarfs and nebulae left behind after supernova explosions. These observations give scientists a front-row seat to the life cycle of stars, how they are born, live, and eventually die. But maybe one of the most exciting capabilities of JWST is studying exoplanets, planets that orbit stars outside our solar system. Its instruments can analyze the atmospheres of these distant worlds and look for signs of habitability, or even life. One major find was LHS 475b, an Earth-sized planet just 41 light-years away. It orbits its star in only 2 days and has a thick atmosphere, possibly made of water vapor, carbon dioxide, or methane. JWST has also examined other exoplanets with very different atmospheric makeups, some with clouds of hydrocarbons and others dominated by hydrogen and helium. These discoveries have expanded our understanding of what alien worlds might look like and the different conditions that might support life. And JWST is just getting started. As it continues to collect data, it will refine our knowledge of planetary systems, explore potentially habitable environments, and fuel the ongoing search for life beyond Earth. The JWST is also helping us understand supermassive black holes, those giants at the centers of galaxies. These powerful objects shape their surroundings in dramatic ways. By observing their behavior and interactions with nearby matter, scientists hope to learn how black holes influence galaxy evolution. What makes JWST even more special is how its technology is already benefiting fields beyond astronomy. The precision engineering that went into its mirror alignment and sunshield design is inspiring advancements in medical imaging, environmental monitoring, and telecommunications. The telescope is also helping us dig deeper into some of the universe's biggest mysteries. How did the first galaxies form? What is dark matter and dark energy? Can we find biosignatures, like oxygen or methane, in the atmospheres of alien worlds? One of the most striking JWST images comes from the Tarantula Nebula, in the Large Magellanic Cloud, a colossal star-forming region. JWST revealed glowing gas filaments, clusters of new stars, and remnants of ancient stellar explosions. It also captured detailed images of iconic regions like the Eagle Nebula and the Ring Nebula, offering both beauty and valuable data. The James Webb Space Telescope is more than a scientific tool, it's a symbol of human curiosity and innovation. It brings us closer to answering age-old questions and challenges us to ask new ones. As it continues its mission, it will no doubt shape the future of astronomy and inspire generations to come. Are we alone? How did it all begin? Thanks to the JWST, we're finally getting closer to the answers.